Sí, creo que sí, soy todo, ¿no? Sí. Ay, Dios.
Maybe you can wait. I think I'll wait. Yeah, also you got really done. But we can have it late lunch because it will be around.
When I change to Christmas time.
Usually the other lecturers like 3-4 minutes. Five minutes late, so I think some students yesterday went out.
I don't know.
Still, I surprised a lot.
Es porque me corre justo cuando te voy a cambiar de curso. Acá no sé si so I discussed illustrate how you practically use it. I do it at it was okay, but So it's a university, Tuesday University of Lyon, but because we're working together, it's really nice. But I have converted only 2 years ago. Because you also have the big enough to get this excellent
Okay, so maybe we should start to make a big delay. So Franco and I are really happy to have today here Elise Dumont. Elise graduated from the École Normale, Supérieure de Paris in 2003, and then she obtained the PhD years later from the University of Paris. After this, she did several postdoctoral studies at UCSF, Australia National University, yes, and the University of Nancy. Then she was appointed as assistant professor in the École Normale Supérieure de Lyon. And in in 2022 of this year. She was appointed as full professor at the Université in the Institute of Chemistry of Nice. And her research interests are the study of binding energies for protein ligands and cross gas. And now she's working in olfaction science, which I really don't know what it's always about.
I will tell one word about it.
Okay, great. So please, Elise.
Muchas gracias, Inés and Juanro. So it's a pleasure to be here and to see you to discuss a little bit about a name you may have heard of, this QMML. And so I will say it at the ground state. So for those of you who like excited state, don't worry, just after, it will be time for excited state. So I will just introduce a bit of the basic concept of it. And you may know that almost 10 years ago, it was awarded this QMML method at the Nobel Prize, that was given by Carpus, Levitt, and Warshall. And it's like if you check the publication, you are going to tell me that, yeah, it's not so much increasing anymore, right? It's still a lot of work, a lot of beautiful study, but I will try to give you a taste of it today in this lecture. And also, if you check overall, like multiscale and onion, actually the trend is still getting high, so you can be happy with the fact that we can still do nice things with that, okay? So is it useful? I will try to prove you that it is indeed something that you want to do, and you want to do it not only because you want to be cheap on the calculation, but also to try to decompose effects and to get an idea of, for instance, enzymatic catalysis that I will talk about a bit today. This is not really QMML, and you had lecture already about that, so it's just a recent paper that I will give here, and you see that you can do different biological systems, and I will focus my lecture on biological systems for QMML. So from the history to now, it stopped in 2015, but now we can do extremely nice things that I will show you. The question is, why do you actually need to have to couple two methods, which are quantum mechanics and mechanical mechanics? This is taken from Marshall, so you may not be familiar with biological systems, but you have seen a bit before. So now the question, the key thing we want to do is to describe the electronic phenomenon, and it has to be in some region of space. It has to be contained. So for instance, here I would like to know what is going on with this histidine. There is charge plus, it's interacting with this aspartate -1, there is water, there is alpha helix. The question is going to be, what do I want to look at? So me, I'm going to look at reaction, but also perhaps charge transfer phenomena. And I want to study a reaction, but not only, it's going to be strongly tuned by the environment. And I will give you an example to feel that a reaction occurring in an enzyme, of course, is going to be different from the intrinsic system. So we can summarize here this system to this one. And the first question is going to be, what should be the size of the QM system? So you may think historically we had to take tiny QM systems to avoid the computational bottleneck. But actually now you can do simulation with hundreds of atoms in the QM part. The question is, do you want to do that? Is there interest to do that? And if you want to do it, how you could do it? So I don't say 1,000 at some point, otherwise you are going to do ad initio MD, but you have a question of what is the size, and I will give you a bit of research example about it. And there are also the question of how do we are going to treat the interactions, because there is a response from the environment. So it's like this big molecular mechanics part for which we have very accurate force field that you have discussed in the previous lecture, okay? And I want to get an idea of this description of this low-level subsystem. In different papers, they can call it the outer region or the low-level subsystem. There are different names of it, but as soon as we agree on what it is, it will be fine, okay? So this is the NN part, and this is going the system where I need to describe something electronic. And the question is, I'm going to treat the interaction, and also at some point, I'm going to impose something here, which we are going to be a QMML frontier in between the two, but keeping the interaction and the crosstalk between the two regions. If I lose that, I lose everything. So we will see there are different ways to do so. And we want to account for ever a proteic, but it doesn't have to be only proteic. You can also want to do the kind of same spirit in the kind of material science, zeolite, in DNA, in a lot of systems, you can apply the same technique. So you want to do that also to decompose the energy, and we are going to see that the system, the energy, the total energy of the QMMM, it's not the sum of the QM and the MM parts. There are interactions there we need to account to make it actually accurate. So I grabbed this picture from a very nice review I gone off, and here you have an idea how we are going to do that. And we are going to have two schemes that I will introduce. So we take a system here. It's a system where we are going to have a phenomenon of interest, so something aromatic that might be charged or not. And we are going first to describe this situation. So the MM part, of course, is going to be bigger. But we want to have an energy for the QM part. Is it easy to do? Kind of. It's like the question would be, how do I do when there is a covalent bond that is separating the QM and the MM part? If there is no covalent bond, you will tell me it's fairly easy. If there is a covalent bond, I'm going to have to employ some trick to be able to redefine something that is not like a bi-radical. I don't want to work with something like that in my QM calculation, okay? And now, if I do that, I could have one option would be to treat the molecular mechanics. It may be the most intuitive. It's called additive scheme. I will discuss a bit after. One thing I could do, and that is perhaps a bit more intuitive now, is to conserve everything for which I may have actually already ad hoc force field. And then I'm going just to calculate this at the MM level, because, for instance, if this looks like very much like the tyrosine, I have already parameter. It's very easy for me to get that. And then how do I actually? Yeah. How do I? If I do that, so I can do it, I'm going to have a little trick here, which is going to be either a nitrogen atom to saturate. It goes here, this one is fine, this one is fine. And then I already have MM parameter. If I do that, there is a double count. We agree on that. Okay? So we cannot do it. So the subtractive scheme is just going to take exactly the same system as the QM1, but remove the parameter from the MM level, and then comes this easy equation. So the energy for the whole system at the MM level, plus the energy of the QM, minus the energy that we need to remove just to avoid the double counting. It's historically very much employed method. There are some difficulties in that I will mention. One thing I will also say that if you want to do more than 2 layers, it's easy to adapt, and you need to have the MM parameter for that. So you may think this is the case where it's easy. I will just go back a little bit here. For that system, you already have parameter for residue, so it will not have any difficulty. But if you have a metal inside, then you don't really have the parameter. You don't want to do it at the classical level, and then the story is a little bit different. So we can do this scheme, and we will see it corresponds to the Moro-Kumaz method onion, and it's easy to implement, but it has drawbacks I will exemplify. There is another way that you could want to do things. Is just this time I'm going to say in the additive scheme that the energy of the QM system is the energy of the low system at the MM level. This we agree on, and there is no high system level. The energy of the high, the small part that is treated with quantum mechanics, and then the energy of interaction, which is difficult to evaluate. And there are different ways to do that. So 2 easy terms, but you already know how to compute, and this one we will spend more time discussing it. So you have different ways to do that depending on the embedding, how you want to describe, and we will spend some time on that. The first thing that for reason of implementation and also to be able to do it, it's called the, sorry I'm French, à la MM, so molecular mechanics style. We are going to do this electrostatic interaction that depends on the electron, and we are going to take inspiration for what is going on at the mechanic level. So this is how this term here that you will see on the exam just this afternoon is going to describe the communication, the crosstalk between the QM and the MM part, and I will spend some time on that. But just like for now, keep in mind, this term is really important. If you don't have that, the QMM calculation is actually worse than anything, okay? So this is from the review here. Sorry, just. Forgot one thing here. the big advantage of this one is that if you want, you don't need parameter for the low-level system. So it means that if you have something a bit for the high-level system, we don't need classical parameters. So if I have a metal or something and I don't know really how to derive parameter, or they are not really straightforward, then I don't have to do it. So that is the good point of that method. Okay? So here is just a representation, and I will show many different systems here. Just to give you a taste of what we can do, like the QM region, I don't mention specifically the method, but it can be not only artifact, DFT, and semi-empirical, it can be every QM method you want. So now there are many interfaces in different codes that become so popular. Everything for excited state will be mentioned by Igor just after, but I will mostly for enzymatic focus on semi-empirical and DFT. Artifact is doable, but you probably don't want to do that for obvious reasons. You can also do MP2. I will give you a bit of an example where it could be useful. And then you can have whatever program, whatever force field you would like. And the key question is how to describe that term. It's not so big, but it changes a lot across the reaction. So we will see practically how to choose the QM region, and the limitation that was historical for computing reason has lowered down quite significantly. How we can just like couple and recouple the QM and ML system. It's not perfect. There are still a bit sometimes stuff missing, but it's the price to pay to be able to treat very large system and how to readjust a bit the force field, which remains an approximation of this method. So here to describe the CAD system, I will not mention it, but you always have water a bit around, and then you have the protein that you don't want to get. And here is the question how to select a set of residue, and I will show you also, for instance, on DNA, which the practical will be. So if we want to write down and implement, this is the way it's going to be. So I have the energy of the full system, and it's going to be the term of QM that we know how to treat. This is just mechanical, and I just multiply by 1, so there is no difficulty. And here it comes the problem, the term that there are different levels of, you can have proposition to do that, because this is a trick, this is not something physical, so there might be different ways to write it down. And usually we are going to write it, as I was saying, mechanical molecular style, so LIMN. So you are going to write it as an energy of stretch plus an energy of bending plus an energy of torsion plus van der Waals plus here something that is electrostatic. Just because this is the way it's easier to implement, this is the way that actually works. And then we are going to redefine all these components that actually come from the force field but are going to be helpful for us to have this QMMM. And there will be also the nuclear component. So we want to have this thing, bounded, non-bounded, just the way you know it, it's going to be the same choice. And it's an assumption, but also a choice, because it's going to be easy to handle, and we count a little bit when we do QMMM sometimes on the compensation of error. So this is for the additive scheme, and subtractive as another. I will show you different examples. So when we want to do that, so going back here just to provide some illustration for that term here. Stretching, bending, torsion, and van der Waals plus the electrostatic that is going to be very important for this system. Biologically, there are a lot of charges. So when we zoom here, I was not mentioning that much what is going to be happening here. Because here there is something that I have to treat to find a trick, or I have, well, people in the past found tricks to describe that region here. So we will see how this is. So I can define here, even if this atom is QM and the other one NM, I can still define a bond strength and introduce a parameter. That's not too difficult. I also have to recalibrate the angle and the torsion. And once I do the Lennard-Jones, normally I'm fairly happy with that, and I have everything that corresponds to the mechanical embedding. So I have this bonded term already. We will see after what happens when, if you are, for now we stay static, but if you have a dynamics, you are changing a little bit, but I won't say so much. So when you're doing this, you should be able to introduce this parameter, or the program may want you to describe this, but normally if you are working with a protein, it will just take the same one that the one of the MM without modification. And sometimes it will do it without telling you, so you have to make sure everything is going, you are under control, let's say, okay? So now we are going to the case, so let's just go back a little bit here. Imagine that you are just a QM part that is going to be like and here everything will be fair. The problem is along a given bond, and if I want to artificially say for the same molecule, I'm going to take a part that comes from the mechanical and a part from the QM, I need to have a trick to do that. And the most used, and it was sometimes historically, it has been a bit contested, I will show a different approach to say so, but what you could think of, and it's a bit natural, well, I don't know if you can speak about natural when you say QM, but here what you can do is to take zoom here, we want to get this carbon-carbon bond. We want to say we treat this one classically. It looks like a residual, right? So this one is going to be classically, and this one is going to be like treated with any QM method that you want. You could think that, okay, I'm going to describe this CH3, it's not difficult to enforce, but then I'm going to say that this system here, I could compute the energy, I don't want a radical, so I'm going to have a nitrogen here, and if I have to choose and to make my QM program happy, I don't want to take a distance between this C1 and this HL, but it's too different from the one that I know, which is 1.09 angstrom, something like that. So I am going to introduce a virtual atom that I will place here. So this is like 1.5 or something like that. At 1.01, I will introduce exactly here a nitrogen atom. And then if I do the QM calculation, which is by far the most sensitive, I won't have a radical, I will have saturate this dangling bond, and I can compute the QM energy. Even the system is bigger, this is just the trick that we are going to use. And now if I go back and I think of my NM program, it's not going to be super happy, because now between C2 and this hydrogen, the distance is going to be super short. But it's mechanical, so the program won't crash. So we have to favor one of the program, and when you choose the link atom, actually you are going to have to choose a ratio. The ratio is the distance between C1 and C2, and you compare to the distance between C1 and HL. And normally you favor the most natural distance for CH. Because doing so, you won't frustrate your QM program too much. So for DFT, it's not too bad, but if you want to think you're going to do a like excited state and stuff, the program can be, and this is done for you. I will show you in the hands-on how it's done. And link atom, I would say that it's around perhaps 90% of the QMM simulation program. They all rely on QMM, okay? Link atom is stable here. So this one you need to know. So we choose a distance CH that is too small, but that is not going to enter any numerical instability. And for now, thinking of a distance, we have found a trick, okay? So we are going to take this energy, and there is a problem of double counting. But there is another problem that is going to come, and I will describe later. It's just if I take all the point charges of the MM here, of the QM part, and I think what they are used to be in the MM, it may be not exactly be like it's going to be an integer probably, but in the MM world, it's going to be a fraction of charge. So here I will see that you have to redistribute and so on, but here in the QM part, the sum should be an integer, but if I'm going to redistribute, I will have a bit of a problem. So for instance, if you put, of course, a charge here, you could want to do that, it's going to be too close to C2 and it may create some difficulty. So we need to redistribute this point charge, and I will see how it's done. And again, it's done for you. And you have to be careful sometimes because it could be a problem, but this is something that normally it's done automatically and you want to have a control. And there are other ways to do so, because in the case you cut this kind of bond, it's very natural, but I will just come back to that and to see that in some cases you want something more sophisticated. Here comes the most, so what I've been describing here is the mechanical embedding. So for instance, let's see that you think of not really a base system that is schematic, but if you take, I don't know, like a die, I can take a die, but the quantum is okay. I have two helices, and then there will be a contraction, a mechanical effect, mechanical constraint. This I can describe as a force. But I don't describe even if it's neutral system, just the compression of the fact that the protein normally or the DNA is going to have a mechanical effect. I will discuss on system, it will be a bit easier. But this is just something that I could describe just with ball and stick without charging so much into consideration. But now there is something, and we can just give a bit of example, but every point charge is here. And there are many in a protein, and also in DNA you have the phosphate and so on. We are going to talk about the QM part. So we are going to influence and change the electronic cloud here. And we want to add this answer also in the calculation. And it's easy to do. And it's done in almost any code now. You cannot just work without that. So it's the effect of the point charges of the MM towards the QM part. And it's easy to check. You can just check a spin density and turn off the charges and check, compare. So this spin density where these things turn on and things switch off. And it's very different. So the QM part is going to be strongly influenced, sometimes too strongly. We will see that also. But here, this system, this QM system is going to experience strongly the interaction. So there are many, many charges. So there is a kind of a screening that also come into play. And we have this term here that just corresponds to what you know from a long time ago. So a term that is mixed here, that it corresponds to the nuclear repulsion or attraction. I integrate the distribution here, and then I have also this energy. So electrostatic is almost always included. And if you don't have it, the result is very surprising. You realize normally very rapidly that something is going on and it's probably not good. It's good to add it. You need to add it to have good results. What is also interesting sometimes, I will give an example, is to turn off the charges here and see what would be the system without the environment. So for instance, if you want to have an enzyme, you will want to reproduce the experimental data, you want to convince yourself you're able to do that with the price of the approximation that I mentioned, you could do that. And then you would just want to say what was already the QM system, just mechanical, for instance, and just forget about the charges, and then you have the decomposition of the effect. So the mechanical constraint, but also the fact that we have a sea of positive, negative charges, and their position that can change over time, that's another problem, is going actually to change dramatically either reaction or whatever electronic process, and that's something we want to do. Okay. So we have this term, it doesn't cost much, and it was included even in the historical version of the code. So here we have this possibility also to switch off easily, and we see that during the L1 also. So we have this thing here, and I will discuss a little bit at the conclusion time, because this is something that is more a current trend in QMMM. If you think about this, you will think that once I have done some reaction here, the MM charges may change. They should change, okay? If I just transfer, for instance, a proton from here to here, I will give more example later, but for that it's good that it's not, we don't think too much of the system, but more of the method. If I transfer a proton, there will be an answer from the MM and a reorganization. And if I think about that, of course, I can do a bit of an optimization of the dynamics to get an idea how the protein of the biological system is going to change once I do a QM process. But it's not only mechanical. Probably if I transfer some charge or if I do any actually QM phenomenon, these charges are going to change. They are going to change position, they are going to change size, which I didn't really draw here. But you can think of it a little bit like a Christmas decoration, on and off, and charge and changing. And this we may want to describe the problem is that the cost of it used to be very big. So it was perhaps 10 times more. So it's possible to do it. It's actually tricky. You have many codes that are beginning to do so. I will give you recent example to give you a taste of what could be the nice performance. It's getting easier, but there are also tricks. So you want to do that. Just not to want to, in electrostatic embedding, you have to treat the charge, your point charges of your force field turning the reaction, influencing here the electronic phenomena. And now, once we have this electronic phenomena, there should be an answer from the MM, and this is much difficult to get, much more difficult. And you can think that it's local, but actually it may not be local, and it may just be at long range. So it can be an allosteric phenomenon because of the QM, but this is something that we begin to reach the, let's say, the limits of what QMMND can actually do, and I will talk to you about QMMND. So just to summarize, I have introduced normally what is mechanical embedding, electrostatic embedding, and polarizable. And in some code, normally, you don't always have a polarization. Or you have artificial ways to correct for it that are quite good, and we will see that in the hands-on, but not a proper complete treatment. So that's also the price you need to pay for reducing the QM part. So I will begin to continue to illustrate this big notion of QMMN, but taking concrete example, because this is where actually I think historically people begin to feel the limit of the model and continuously begin to improve the field. So this is a system that was, it's a protein, okay, so it's a thioredoxine. And the QM reaction is actually a little hard to describe because it's an electron that goes on the disulfide bridge, and then you form special bonds that are free electrons. They can detect experimentally. Once you do that, the first feature is that you increase this distance from 2 angstrom to like 2.8. So you have 1 angstrom length, so a mechanical effect. And you have also a transition of UV spectra from 230, something like that, to around 420, that is very characteristic, and that is related to this increasing of the distance between the two substrates. So you can study this, and actually you form stable adduct, and the reference energy, the adiabatic electron affinity, is around 0.1 eV. And to do that with DFT, it's very hard, and there are only modern functional, when separated functional, that are able to give a proper assessment. And the situation for that is to do MP2, and you may understand why. It's because it's free electron bound, so you have a lot of static, you have a bit of static correlation sometimes, you also have a lot of dynamics. It's not really done to do so. So we wanted to describe this reaction, first for small systems, very small systems, to begin to feel the mechanical effect. And so this would be an organic change, just like something very natural. So I'm going to have the elongation, and I can think if I just constrain this system a lot mechanically, when I form the electron, I could stabilize this value, which is already slightly positive in the gas phase. So now I'm going to check, this is just my naive picture at that time of the peptide. So there are some different shapes, the shape is irregular. And here I may have hydrogen bond inside, and once I form, I'm going to have this semi-bonded system. And then I may break a hydrogen bond, but perhaps if I play around with it, I could actually tune this reactivity, which is the addition of an electron. So we know that adding an electron, it's a bit more tricky, especially in QMMM, than adding a positive charge, because we are going to have problems with that I will illustrate. So we have effect from a mechanical embedding, and we may have electrostatic effect. So this is an enzyme that is actually doing so. So this is a thioredoxine, so it's a molecular way of stuff. And you have a disulfide, and it's easy to see because it's really like you have all this fold that is characteristic of this family of enzymes, the thioredoxine fold. So we begin the protein here, a lot of beta-barrel, free helices. But what really is interesting is that if you change also the 2 residues that are here, you are going to change dramatically the reactivity. We wanted to see if we could predict that and explain it with QMMM. So now it's time to look a little bit what the code can actually do for you. So I just grab it, and first we begin with organic small system or just like peptide style. So the first thing we wanted to do is to see if I take a small system here, a very small one, just like the linear dipeptide, what is the price I'm paying for this electron affinity, and we take a small system because we want to address what is the difference here between the intrinsic full system. So if I do an MP2 calculation or a couple cluster on a small system or a big basis set, I will get to the experimental value. I just want to know if I'm taking, so this system is a dimer of 16 that is just for now linear, and I'm adding the electron and it goes straight on the sulfur atom. So I can just do the most easy, if I just want not to have NM parameter or so on, is to do onium and to do QM price. So it's like QM, but I'm just not going to have any parameter. I don't want that for now, so I'm going just to say to the, so this is just a Gaussian, it's implemented, everyone can try. It's like I'm going to set up the first level of theory, put 2 points, and here the second level of calculation, and we'll see that a little bit more on other example this afternoon. And here I'm going to say, so H stands for high level, and L for low level. And the drama is that here everything is done for you a little bit blindly. If you don't check, you will just get energy. But we can see what is going on. So for instance, here, what it's telling me that it's going to have an energy here of a low system, an energy of a high system, and then the energy of a real system. So it's going to give me this energy. And then the extrapolated energy, which is the subtractive method that I mentioned before. So we can take a little bit more time here. So here it's for the neutral one. I did the same for the radical anion, put it just like -1 and 2. I re-optimize. Here it's just here a similar system. The difference here is that I'm doing another basis because, of course, this is a small basis for doing this reaction. There is still diffuse, but it's just double theta. There are specific basis sets for electron affinity that were proposed to have and usually employ rectifiability, so we change the size also of the basis set. And if I, what now, Onion is going to tell me, back here, it's going to tell me that it's going to be a cut, which is the QMMM frontier between the carbon and the hydrogen, actually between 2 carbon, and it's telling me between the C2 and C7, I'm going to put a virtual hydrogen here, where the factor that I mentioned, that is 0.7 something, is just the distance of CC over the distance of CH compared to distance of CC. So it's done automatically. You see in the overcode, I have to specify it myself, but now it's just going to be done for you, and you just want to make sure everything is going smooth. And then the second boundary, and it corresponds exactly to this one here, which leaves me with a QM size of 8 atoms only. No, sorry, 10, because if I count the link atoms. So here I have 8 atoms in the 8 part, but the total atom in my QM zone would be 8 plus the 2 hydrogen that I use to ensure communication between the 2 regions here. So now it's going to give me difference after some work, which I split here, and I'm going to have the method, the low method, which is R3 for the energy of the model system, the energy of MP2, the high method of the model system, which is lower in energy because then I take into account the static correlation. And now it's the energy for the whole system, and this value is the extrapolation, and you can check if you want, but it's just this value here minus the difference of this one. So you see, this is the easy calculation. You could, I'm sure you could tell me, you could have just paid the price of the MP2 for this system without problem. But what I want is to see what is the effect of decomposing and using 2 levels of theory for this molecule before I go to the protein, okay? So we did that for actually a series of peptides, and then comes the question, we asked ourselves before the referee asked for it, but we don't know where to cut. And this is one of the big questions in QMMM. We could say, so here you have a cyclic peptide. X is the number of the residue. So I generated some of them from the biggest one is 5 here. We could change after the residue, but it's not so much the point here. This is the reference one, the cyclic one, but it's just the cyclic cysteine. And now I have the closure constant, okay? It's experimental here. And now I can evaluate this electron affinity. I can think that the more I constrain the system, the easier it is, and it's not so much an effect of the, like there can be contribution for other atoms, electrostatic, but also the chemical force and the mechanical embedding as I release. And I want to compare here the so it's a little perhaps tiny, I've just described a little bit, but now if I want to describe the whole system, even for this system in equal 5, it's going to be a little big, and I probably don't want to do that because I want to go to the protein. So I could just say the cut I use is the green one with wavy lines, and it remains just that. The problem that I could see is that it's not sometimes as easy to cut when you have them the kind of branching here. It's easy to cut alkane. But if I want to cut here, it's perhaps not as easy because there is a nitrogen. But we first make that choice. If I go one stage later, then I have to cut two different bonds, a CC, which is not polarized, and a carbon nitrogen that if I'm going to introduce a nitrogen atom just right here, it's going to be very close to the nitrogen. And the problem is that carbon nitrogen, it's not purely covalent, it's a little bit polarized, but CH is going to be really something close to CC. So I'm going to have an artifact that comes from that. And it's also the same thing here. So this one will be rather easy, and this one difficult. And when I say this one is going to be rather easy, here I'm going to have a H that could be a little bit close to this CO, so it's getting a little complicated. If I move again, then it begins to be a red flag because I'm going to cut something, and here it's a nitrogen carbon. Again, it might be a little bit difficult. So we did this calibration with different force, different basis set, we try with DFT also, just to see what is the answer. And the conclusion was that actually it's easy. It's not a big problem to cut very close, but we have to favor a carbon-carbon, and then we replace by the CH, but we have this first result that actually we get a similar electron affinity. And what is the reason why we get this 0.5 reference value? It's also because we have a compensation of error. So this is just the difference between the energy of a radical anion minus the energy of a neutral. And if I get this, I'm just going to use the frontier for the two systems. So this is a case that is perhaps not as difficult, even if it's close and cyclic, so there might be some interference because I'm removing between the radical anion and the neutral. I should have a kind of compensation. So we have this system and we did this calibration. And now comes the beautiful part where we can actually predict results. So we have this enzyme, and I could compute the electron affinity, but it does not compare to a redox potential, and I don't have a redox potential because this is an electron, this is a transient species that I'm looking at. There is no way, I think, to measure it easily. What you can measure is the redox potential for the SS and the two systems, which would be SH-SH, after two electron transfer and two proton transfer that are probably coupled. It's a different story. It's much more, it's not really what we want to look at here. And it's certainly not easy. So we are going to look at this system, and it's still, we can do the calculation, but the problem is that we get one value, and we are just going to want to tell a story, right? We don't have any comparison. But what we could try is here in this big system, what makes it really like electron. And we have been building this system here. It's just mechanical. The fact it is cyclic is very important to enhance the formation of this transient species by adding the electron, because you release the mechanical closure energy you needed initially. The proline here is making it also a bit more rigid. And then we begin to grow helices. So we can do it towards the N part or towards the C part. So here in red, it's the energy when we turn off charges, nothing is changing, but here, as we begin to grow the helices, we are going to form a huge dipole. And this dipole has here a positive charge and here a negative charge. We can just think of two big charges, even if in the force field it's not described like that. And now I see that from the reference that were already higher than 1 electron volt because of the mechanical effect, I'm adding an electrostatic effect. and I can reach on to like 2.4 eV. So I can choose the reactivity in a dramatic way of this enzyme, favoring the electron attachment for the mechanical constraint. But mechanical constraint, I cannot really play so much with it. At some point, I'm out of control. But I can draw an Elise here, and because it brings a big dipole, it's going to create this big difference here. And the way I can prove it is that you have this system here, and I can turn off the charges, and then I go back to the red one, which is purely with no electrostatic embedding. When I turn on, here it goes higher, sorry. And if I go in the other direction, here comes, basically I can assimilate this alpha helices to a minus charge and a plus charge, and it's going to decrease very strongly. And what the enzyme shows is to be on the N side, and this enzyme, even if it has, I say, a fold that is important to maintain the structure, every effect from the protein come actually from the green alpha 2 helices. The rest does not play. There is a compensation. We need not find it. And this system, for any color 12, has a similar energy than this big system here, which opens perspective to design systems that are more prone to capture electron and so on. And the nice thing is to be able to decompose. If I had been able to compute the full QM part, I will not have get this effect of what is going on to tune this reaction. Okay? So now we are going to talk about a bit of a different philosophy that could look easier, but it's not easier. So QMMM is also very used for spine solvation effect. So I will illustrate what I call here about fan effect, but the idea is that if you want to have an electronic phenomena describe a solvation, you may be tempted to do a QMMM. The very good news here is that what could be natural is to take your solute and surrounding solvent molecule at the QM level and then the MM. The very good thing is that you don't need to artificially decompose that much. You don't need a link atom because you won't have covalent bond. So it should be easier, but it's not. Because they are fine effect observation, and I will give some example again about radical chemistry. So here I grabbed this citation from Ibarini et al. For system as large or protein of DNA fragment, the original assumption that continuum model provides a cheap way to introduce some of the effect is no longer valid, as the computational costs for the solution of the polarization equation, and in particular, where the linear system obtained with some discretization technique can be covered for very well. So I will not describe into it like the continuum method, like PCM, Cosmo, and so on. But here it's a comparison of what you can do with QMMM to assume the relative free energy of hydration of a series of small compounds, and you compare to what you can have here with a PCM style, and you can see that actually the continuum overperformed the QMMM. But it was first a paper of this old, okay? It's a review from Gao from '96, but it also tells us that there might be room for improvement. The first thing is that IM1 is maybe not the best scenario, and we can see what has been done in the solvation world to improve the situation a little more. So I'm going to change system, not going to the classical one, but something a bit more electrically funny. So it's a radical again, and it's a bit of a signature here that you have two forms of this nitroxo, and they are going to be like it's an odd system electron number, and then you can also have the zwitterionic form. When you see that, when you write this Lewis structure, you will get immediately the idea that the signature with the solvent is going to be very particular and cannot be like calls for some fine QMMM description. Here is one of these nitroxo system here, and in EPR actually you can have a difference between hexane and water that you may want to reproduce. So how you can do that? Actually, you have a system where you are going to use a method that is good for radical. It could be a DFT with some high exchange. It could also be like a MP2, or if you don't want to stick with DFT. Then we are going to have to describe very carefully the solvation here. So even with water, not too difficult, with hexane It's doable, but they are going to be already bigger. Define the zone here. The big problem is here not the solute, but how many water I'm going to put. And then I'm going to need to describe it to some larger extent and begin to have this 3-layer scheme. So we could do a QM for this system, probably just to account the fact that it's all the electron also. QM prime with more water or more solvent molecule, and the rest with MN. And one of the difficulty here would be that we are not going to be able so much to have, if we do a dynamics of that, we won't have so much exchange possible between the different parts. So the good news is that we can just like delimitate and we don't need link atom or stuff like that. The problem is that we have to artificially say how many water, solvent molecules are going to be important for the reaction. So it's possible to do that, and then you need usually, the key take-home message here is you need polarization. I will give a bit of other example, but then you need polarization and basic, and electrostatic is not enough because you don't have a big electrostatic effect of a protein and you're looking at something that is more fine. To give another example and staying still at the ground state, so this is a recent paper that develop polarizable embedding, and so they are looking at small systems that are extremely, like you have a lot of dynamical electron correlation here, and they search for the IR spectra, either with PCM, the experimental is here, you can see that it's really very different, and then they use with a QM method that is going to be also polarized, and they get it quite fine, and then they add some dipole, and it's not really perfect, but already you can see that there is some nice recovery here, and they get the right assignment for the normal mode shown here. And the price to pay for that is the polarizable effect. If I stick on something not polarizable, I do not have comparison. Another example here, a bit more biological, and here with QMMM and a correction for polarization. So in this enzyme here, we are going to look for different states of the cofactor. So experimental is the red curve for this IR spectra. And then theoretically, you are in quite good agreement. Of course, in the low mode, it's always a bit harder because you have anharmonicity, but you have a decomposition of the effect that experimentalists are trying to look at. And to obtain this spectra, they truly need, again, the polarization, which is the answer from the solvent world, the change of the solvent upon the modification of the QM part. I focused, I say things about biological systems because it's my expertise in terms of research, but I have to say and to acknowledge the fact that there are many recent developments to describe also fine solvation, this time not between a solute and the solvent, but between either a metallic interface or nanoparticle, and communicate with different codes, such as crystal here, that is periodic DFT, coupling with amber, and trying to describe this part, the QMMM, with IFC that is developed by a Danish group, the Atomic Simulation Environment. There are many exciting things, so I would say that the interesting point is that initially when we were discussing, I come actually from a group I used to be heterogeneous catalysis a lot, they are experts in that. When you talk to them, I would say 10 years ago, they will always stick on ab initio MD. They will not believe in QMMM for something else that's not biological. The thing is that you can parallelize very much, you can have all the plane wave that you want, were really like used to it. But right now, the trend is probably to try to develop new QMMM scheme to be able to treat this system. And of course, here, when you begin to have metals, the response on the solvent is going to be very challenging to describe, but they are encouraging use towards that. So this is a place, I guess, where we are going to have from the solid people and the material science community new opportunity to reach the fine-tuning here. That is also a problem to get in QMMM, even if you don't really have this flash here. So it's like a bit, you don't have so much link atom problem or frontier problem, but the problem really comes from the polarization of the metal atom that you need to describe finely to describe also redox potential or electrochemistry and even actually photochemistry. So they are changing and they are the reason also to be able to change is to be able to describe much at longer range time scale the reorganization of the solvent. So because in ab initio MD, you have this limitation that is a little bit hard to pass. So I changed system a little, and we are moving on to the system that we will discuss like this afternoon together. So this is DNA strand. And there are many DNA current, there are so many investigations, and it's crossed by DNA repair, usually when an enzyme, also the formation of DNA dimer, DNA charge transfer, and there are many things about the photochemistry of DNA, but I don't mention because Igor will have just introduced this method just shortly after, but you can also do everything with fluorescent probe, for instance, photoreactivity, photosensitization. This system should not be too hard to cut because you have a kind of regular motif. It's not like a protein. It has a nice B-helix form. It should not too that hard. But the problem, one of the problems here, when you try to think where I'm going to cut, is that you have a nitrogen and here a carbon. So there is a polarization. And if I want to describe one of these nucleobases at the QM level, if I want to be perhaps ambitious, I could just take the whole nucleotide here, including even the phosphate. Because I want the charge of the phosphate, I could think that it's negative, so it would play a role if I want to study at a given phenomena. And if I do that, of course, I also need to include the sugar, and it would work if it was isolated. The problem is that if I do that, I'm going to cut here and to cut somewhere over there. And then I begin to cut something that is a carbon-oxygen. And I told you that the most polarized the covalent bond, the harder to cut. So we want to try to avoid that, because here if I replace something that is carbon-oxygen formally by carbon-hydrogen, I may lose something in the process. So I want, the first thing we could do is just to cut here, and the carbon-nitrogen is not terrific, but it's the best we can do. And also what is a little difficult is to enforce a nitrogen here to be a little close from a cyclic moiety. So there are different ways to do it, but it's not the best system. And also you can say, okay, I want to describe this nucleobases, but sometimes you can have radical reactivity towards the sugar here. So then I'm going to include the sugar in the QM part with the nucleobase. And if I want to study this, then I need to cut somewhere here, but cutting close to something negative is not always a good idea. So this is another system where I'm going to have a problem a little bit of the partition of the system and where I can impose something without being too drastic. Yeah, I will go to introduce. So this is the kind of a system where people begin to think that they need other schemes than just link atom, just because there is no easy way to do things. So there are three ways, to my knowledge, in the literature. So when I want here to separate the QM region from the MM region, I'm going to have the possibility of a link atom. So here, it's usually a nitrogen. There was some suggestion to take something a bit different, like modified reagate or something. But we can do the link atom, and as I told you, it's the choice for, I would say, 90% of the simulation at least. Another possibility to avoid replacing this XY by something that is CH that is not polarized is to replace this bond by an orbital that is going to be frozen. So you have an example here. So now I'm going to just like take this sigma orbital XY and constrain it, which means that I cannot re-optimize everything in my QM world. I have to freeze an orbital, actually a couple of orbital bonding and non-bonding. And then we do the calculation, and it will stay at the exact distance because I'm going to constrain that specific orbital. So when you do that, usually you have to redo a lot of code, but it was done by design in the 90s. It works really nice. When you want to do that, you are going to keep the same distance here, and you are going to have formally something that is more elegant, but the setup is also more difficult, and the drawback is that if you want to change something like in the dynamic, you cannot redo the calculation of the time. Okay? You have to specify. Also, this orbital works nicely, but sometimes you have to localize it very specifically to a strictly localized bond or extremely localized bond process to just make sure that the connection is described as accurately as possible. On some cases, the error that you pay for the QMLN frontier is going indeed to be much lower than the link atom. And there another way that is similar in the spirit here is just to re-describe here the X atom by keeping an active orbital and just auxiliary. So this is a generalized Aldrin orbital that is in the spirit very close to the self-consistent field that proposed by Trivalet. So link atom has become a bit popular. So here you have another illustration of this one just here. So I'm going to describe this in the process. You can combine and add actually the link atom, but this is more subtle to do and more adjusted when we, for instance, if you want to get carbon oxygen. Now we can check at the dissociation curve here. So we have this bond that is extremely localized between the QM region and the MM region. And you can add here a frozen core orbital, and we check compared to the fluid QM. You don't have the value here, but as we dissociate even the carbon-carbon, you can see LFCF is not perfect, but it will be the same for link atom. The question is that when you do that, you have to keep in mind its compensation of error. And if I use a refined process for keeping the boundary, I'm going to have still this difference. And I can just use a frozen core orbital to decrease, but this is in the static region. When I want to have something that is done a bit more automatically to begin to include the dynamics, which we will see in the second half of this lecture, I cannot always describe that as easily, and then the solution is more for link atom. So what I will do is I will say we have like a 4-minute break, and then we move on to the second part, okay?
So here is carbon, so between this carbon and between this carbon.
This is okay, but the problem is that if you do that, and you agree with you, it will be easy, but if you have to do it at another stage also, and then it has to be symmetrical. If I cut it here, I cannot cut there, I only cut 1 notch before because I need to maintain the size of the nucleotide. So, but I agree, it would be wise to do it, like here and here. And actually, it's also, I would say, after that, if you keep the phosphate in the square part, the sodium that goes with it, or the counter anion, also needs to be. Thank you for the question. Yeah, no, it's a nice question. Thank you. I guess we practical and also yeah, I didn't. I don't think so. The idea is nice to have a system but I'm sure you got to make what I'm looking for. At the time, the partition. We used to get a setup with different people with blindly and then compare because the setup is and now it's actually, yeah, they did the benchmark, they watched the GPC and from that time, I think I will show it in the end, but now you have plenty of code, but if you want to freeze or because they are much less code because you need to like redefine, you need to modify your control to be able to freeze your control and you readjust all of that. So very omnibus, but everything we can do. I will find I don't know where that's in the right.
Just that I'm curious because I don't find it. Put mine in my bag so that in my home. I will like collect all of them. Found I still have the ID here.
I think it's kind of very introduced station
Okay. So we are back here to so this situation I was describing that in some few cases link atom is not going to be favored and you are going to play with frozen orbital and in that case you need specific code and you need actually to modify, to rewrite QM software to be able to just say this orbital is not going to be optimized during the process. So it's codes that are available in some group but not as many. Whereas this implementation everything is like done for you, it's easy, and actually there was some comparison between some methods, and unless you have a very pathological cases, link atom is actually going to do a good job for you. So this is again the DNA, and now, for instance, what we wanted to look at, and it's my obsession to us, I wanted to look at the electron addition on DNA, and there were some results in the 2000 that show that actually you're going to break this carbon oxygen. So the attachment is going to be done on the nucleobases, and then there is a through bond transfer and going to induce this cleavage here. The problem is that then I cannot just take this guanine. So it's not a guanine. I'm going to take this nucleobases as the reference one, the cytosine. I need somehow to describe the process of breaking this bond after electron attachment. And then I need to include the phosphate because it's so close from the phosphate value here that I'm going to have a problem if I don't include. So we wanted to describe that, and the solution we found was to enforce orbitals that are strictly localized because we cut carbon oxygen. And when you do that, you need to redistribute a lot of charges. It's a bit technical. We still wanted to give it a try to be able to let. So if you have a reaction, the message is you cannot just cut just nearby, it's going to be dramatic. You need to let at least 1 or 2 carbon just to let the system breathe a little. So we did it. Here again, I'm going to show some partition. What is going to happen in your code, we will check a bit more this afternoon, so I may skip this one a little bit earlier, a little bit faster So this is done actually in QMMM. Let me just show you. So this is what to give you an example of where we may need strictly localized bond to be able to describe the signal bond breaking that is happening in the region with such a lot of things. So now the link atom has one advantage that if you want to have a system, so here I grab it from the tutorial of Amber for this first example, and they sell it, let's say. It's very easy. You just have your Ember or whatever software you like, and normally you're just going to call the QMMM and select your partitions, so residue 1 and 2 here. You set the charge, you set the theory, so you don't have to like semi-empirical, even if I would try to convince you that it can be a good way to work for QMMM at the ground state. You do shake, you do evade, and you do particle mass evade, you activate it also. So there is no link atom, so it's not really QM/MM. Sometimes we call it QM2.MM, just to mention there is no link atom or not something that is too difficult. And then it's going just to assign the QM region here. And everything works fairly transparent. It's just going to be the same dynamic. You reuse all the code that you know and just to have activated this small thing here. If you want to be QMMM, like really QM style, you're just going to code the external code, like for instance, Orca or Terraform. I'm going to give you an example again about what we can do with DNA here. So here we have a DNA DNA helix, and we have all the counter ion and the water. And what we were interested in is to look at this family here. And you see there is a stack of 4, and you can have a triplet state. And we wanted to know where this density is going to be, and is there some delocalization. So we did that a bit brute force. That's a recent example. So we described this with M062X with a rather small basis set. I will mention it, but when you do QMMM, you may think I'm just going to take, that was also, I don't know, I can admit it here. When I was young, I began QMMM. I wanted to have the best QM possible. And the MM was a decoration, but I was from the QM world. And then I was told, and I arrived at a group of people like developing code in Nancy and so on, you don't want to use a big basis set, otherwise you pay the QMMM frontier much more. So when you read the QM paper, you may think that the basis set is always a little key, but it's a deliberate choice not to have a too big effect on the QMMM frontier. So this is the system we look at, and we did 5 trajectory of 1 nanosecond with something that the QM size, you can do much larger than that, but at the DFT level for nucleobases, it's already something that we're running for a few months, I think, on our cluster. And then we get energy between singlet and triplet, and we try to see what is happening. And we have the experimental value for that system, but what you can see here is that for some trajectory, I can change things dramatically by 50 kcal, okay? So I can have 310, and another trajectory is going to give me 258 for that system, where I have put the 4 timing together. This one is much easier to get. They don't suffer from the same drawback. It's because when you come from free energy world, which I don't, but you tell them that you take some 5 trajectory and you try to infer energy, they laugh, okay? It's not a good way to do it. And that's a problem when you do QMMM ND. Your time is short and you cannot sample that much. So your energy, if you want to really compare a free energy to something experimental, sometimes you will have difficulty. And they are a good way to palliate that if you don't pay the price of the DFT or for other systems. But this can be a limitation. And in some papers, like 10 years ago, they provide only 1 QMM trajectory, and it's so dependent from the starting point structure that actually you have a problem of statistics going on here. So this was a message here that for different trajectory, you may not have the same chemistry, and you are paying the price that this was 1 nanosecond, but we know that for the biological, it's still a rather short time to look at. There is one thing I did not mention slightly, but I will go back a little bit. So when we want to have, I say that we are going to modify the force field. So force field, you know how they are doing, okay? They are compared to QM, phototion profile, and so on, experimental data. They are all this machine learning trying to make new, very accurate one from some machine learning derived for DNA that is coming up soon. And for QMM setup, a priori, this standard parameter may not be added, but we still employ them to avoid the redistribution, recalibration. Also, when we force a QMM frontier, we will illustrate that more this afternoon, but we have to turn off some charges. It was not an integer, and we are going to redistribute, and there are different ways to do it. So we could just redistribute on the ones that are the closest one. I give an example later. We can redistribute not only close, but a little bit further, or we can redistribute on the whole system. Everything is legitimate, but the impact of that on a given quantity may not be negligible. So it's done automatically for you. Before you had to select, but it's done for you, but you can also want to recalibrate if you think this is not exactly accurate. The problem is that if you run a dynamics, perhaps you're not going to do that all the time. So for static calculation, you can do it. And when you are thinking that there are so many degrees of freedom of where you want to have a QM size, the level of theory you're going to employ at the high level, and then this distribution of charge that you have to do, you may think that it's really a lot of parameters, but at the end, you want a constellation of error, which I illustrate, for instance, when you take the adiabatic electron affinity, it's the reference, the neutral system, the radical ion minus the neutral system, it's going to kill off the effect, the price I paid for this thing. Let me show you a bad example of partitioning. Okay, this is still the DNA, and let's say I want to cut here. It's not so good because already it's cutting a cycle of 5 where the frontier, you can imagine that in the end the angles are going to change and my sugar is going to be like torture. But let's say I want to do that. So here it's amber interface with Orca. So I told you it's exactly the same as the amber you like, or you don't know it, but it's the same for other code. And I'm going to call an external code, which is Orca here, and to make a QL mask where I'm going to give the number of this finding. And the code is going to tell me, okay, you are going to do this link atom. So here I did it for the 4 timing. It's going to describe carefully what he has done. So deriving new rest charges, adding the link code. And here it says that it has to do a redistribution of minus 1.382 electron charge. It's more than 1 electron. So, okay, I could say that it's 4 boundaries, so the effect is to be dividing this number by 4, but you see it's huge. And it's done for you, but when you begin to do so, you can feel a bit insecure. You can begin to think it's perhaps not a good idea. So why is that? So here it's because you have a carbon oxygen. And when you turn off things here, you can kill off the charges of the one that is the next close, the first one of the MMR. And this one, of course, has a big negative charge, which you are going to pay here. So the code will not yell. It will not just like tell you this is a bad idea, but the result is not very good. And sometimes you don't see it that clearly. And also, if you do that, the sugar, I'm not a sugar chemical expert, but it looks a little strange because you have 2 bonds close related, not just adjacent actually. And then you have also a geometrical problem and a redistribution problem. But it's easy to fix. So now I'm showing you this partition for a carbon nitrogen. It's slightly polarized, but I don't have any carbon-carbon to cut. And now the charge I have to redistribute is minus 0.235. And this one I'm going to divide by 4, because actually on that system we were enforcing 4 QM parts, which is described a little bit here, between the CT and N star, which correspond to the N because it is bond. So this is one of the parameters you want to check when you do a QMMM, what is the amount of charge I'm transferring, and it's computed for you, but you have to check it because it can be so different depending on the partition you are doing. I've been telling you about the additive and subtractive. So in the history, onion was proposed, begins to have very nice reference result, and people begin to use it. And then people begin to prefer the additive process. Also because in the additive, you have a bit more control, let's say, and you don't have to, you have to redefine the parameter, and then parameter for the high, small zone you want to describe electrically. But here there is a recent comparison on the difference between the two, and to sum up this paper, even if I wish you could read it because it's really a good one, but they say that actually subtractive has a lot of advantages too. And one thing you can just keep in mind is that actually if I have an additive scheme, to make it to 3 layers, you can do it, but it's challenging. But if you want to add this 3-layer zone, it's very easy with the subtractive, let's say, onion-like procedure. So onion is for our own integrated model, but actually they call it just because it looks like an onion, and you can put as many shells as you want. And you can want to have this system, for instance, for fine tuning. You also want to have some active solvent molecule that you could add, describe either with a cheap QM method or something. So the problem of onion is also sometimes that you need boundary at each level, which are not something nice, but you are in the inner calculation, everything is gas phase, this can be a bit of a situation. So you need to know, you want to know if you are additive or subtractive because it impacts the calculation when you are doing this method. Just to give you a word about which code can do QMMM, I was going to show you in the end, but many codes now have QMMM interface. They used to be provided sometimes by QM software, and now the trend, I would say, is more to give them in the molecular dynamics. And you see that the implementation is not too difficult. It's exactly the same one. I'm just not having to have a Coulomb here. I had to take this special term, but it's fairly easy to interface. So to code on your own, and now you have many different, and the comparison is good between code. So I'm going to show you here this very nice paper. We can go to 2019, but describe a bit what can be done for enzymatic catalysis. So I've been describing the QMMM. So it doesn't give protein flexibility, but all the rest is good here. And I will tell you a bit about QMMMD, and I will just say a bit of EDB method. I don't use them that much, so but they are really good also, just being semi-empirical with some specific parameter. I will tell a word about that. There is also the computational cost. So I'm going to give you some example of QMMMD, but the computational cost, it was plus. So they are expensive methods, but still more and more popular. I will tell a word about the cluster model. The cluster approach here, so you can see for this enzyme, it's specific, so for it's doing the limonene epoxide hydrogenase, I think. So you have this reaction here, and you have a very large QM path. And every residue that is here, you need it to just be able to describe this reaction. So for Lin and Imo in this paper 9 years ago, they were able to just they take the enzyme, it's not a QMMM. They just keep a model, and to be able to keep the mechanical embedding on the protein, every orange atom here is going to be constrained. And once they have this model where this the substrate that is really in the right position, also needing a bit of a water assistance, they can derive predictions. So for some systems, it's called a cluster, so it can compare to QMMM, but you don't have any MM, you just find the best model that you can play with. And this is what we saw just here. What is the cluster model? No MM part, not the whole enzyme, but you just reduce to something you can treat fully QM with the really need to have the constraint here. So this is for the limonene epoxide hydrogenase. Another example, just to show you, because in the past QM parts were small. This is not the case anymore, also because it's automatic. So for this repair system, repair enzyme, we have a cofactor here. We have a DNA methyltransferase, and you can see how large the distance is. And you can absolutely just put as many link atoms as you want. And then the system is highly dynamic, so probably you need a QMMM frontier that is not going to be, it has to be redefined every single step. But this is an example of, I didn't count how many, but because I have a system with much larger QM part, you don't have so much of the problem of the size of the system. It's more a question of chemistry here, and to make sure you don't forget any residue that might play a role. So here they always tend to include everything that is electrostatic, so positively charged, negatively charged. Here, of course, what we want to do the methylation here, and the cofactor, but also, for instance, this hydrophobic one, phenylalanine, that is an important one. So this is recent example. This is the record that I found for what it can be the big. I always have this question normally. How big can be the QM size? So I would say it's 940 atoms, but already for dynamic, it begins to be quite big. Okay, so that was done with TerraChem, that is an interface for GPU. So this allows them to do this kind of model. So here you have a very electrostatic. It's a bit difficult. You still have the same cofactor here, and you have the magnesium also. So still for the metyl transferase, they check how many QM residue they can include, going up to 56, and they found a kind of saturation. So you can check the structure, you can check the reactivity. The conclusion is not straightforward because it depends on the property you want to look at, but basically they say that they are fairly happy when they begin to include 11, 16 residue. So they don't need to go to this really big QM system where the MM part is actually smaller than the run system if you don't take into account the water. So they have tested, and this is the kind of example that we were missing perhaps like 10 years ago, systematic assessment as I'm enlarging the QM part, how property are going to converge or not. Okay. So the QM size also, because of computational power, is not so much a problem anymore. There is one question also about the QM level of theory. Here it's an epoxide again here from the group of Normale in Bristol. So they have experimental value very accurate for the free energy of activation and the difference. So they are looking at semi-empirical, DFT, and here you can see that it's fairly far if you want to do any prediction. But if you use MP2, the core of the system described as the spin scale component MP2 with B3 LYP, then you are getting in good agreement. So it's not really like absolutely perfect, but you can have all the interpretation, and of course that system is particularly challenging. But we can have this sometimes if you are just looking to this one and you think what you're going to miss, you are missing the high level, especially for a system that has a lot of dynamical electron correlation. So, and now I was telling you, you can just not stick on DFT or semi-empirical, but if you need to, there is no problem to go to higher, especially, for instance, ORCA, where this array implementation is interfaced with lots of MD. I grabbed this example that comes from Spain, actually, in this book about simulation of enzyme reactivity. Enzyme reactivity was perhaps the most important result obtained by QMM people. So this was to give you a flavor of what they have been doing. This is about SRASCOV2. One of the challenge, apart from the size of the QM part and the level of theory, can just be actually to describe reactivity. When you have that many residue, you just need to reduce the dimensionality for your reactivity. So here you are going to, in the end, you want to draw an electron profile, and so you have here 6 collective variables to be able to find a way to reduce the dimensionality to actually be able to obtain a free energy profile. This is done by B3LYP. You need diffuse function here, dispersion, but the key challenge here is to be able, in the end, to be able to obtain this profile. Usually now we can have them with error bars. We can do a lot of comparison, especially for kinetic isotopic effect experiments that are very convincing to get an interpretation. And the selling point, of course, of this paper was to be able to get better drug and to understand the degradation process once it is within the enzyme. I wanted to say one word. This is the only slide where I'm going to use actually excited state. Shapiro, allow me that one because there are not so many examples. So when you want to do enzymatic reactivity, you need QMMM, and it's very hard to have an enzyme that is very rigid, and now we can just afford this kind of calculation almost routinely. We can have large QM parts, we can have the level of calculation that you would like, and there is still a lot, paradoxically perhaps, a lot of enthusiasm for semi-empirical approach and approaches like AM1, PM3, DFTB that are very popular, and I'm just going to give perhaps one reason why. So why, if you can just like work with QM method, you would like to do semi-empirical? I mentioned it, but I'm going to stress this out again. When you have to do QMMMD, you can just, it's very hard to get 100 of trajectory. You are just going to have, usually it used to be the case, a single trajectory, where I was taking like around 3-6 months, like 10 years ago, depending on the system. But you are just going to believe it a little bit blindly. And it can be very different from depending on the starting point. The starting point is not so easy to describe, especially for systems like DNA. You can have different orientation. They play a big role. If you are ready to just like approximate and get to semi-empirical approach, one advantage is that then you can run hundreds of trajectory. I grabbed this paper. It's not with semi-empirical because I didn't really find something in the literature that that was quite good what I wanted to show you. But here for that example, I grabbed from, I asked permission to Igor Shapiro who is going to be the next lecturer. You can see that for 200, you can add here 2 different stories and some trajectory that are very different. Now, if we think back about the enzyme, if I am doing a very fancy one trajectory, QMMMD, and I'm just going to find this one here, I'm going to make a beautiful story that doesn't make a lot of sense. And perhaps I will have nice energy and so on. But the fact to sample and to be able actually to consider a bunch of trajectory is currently much better if you take semi-empirical approaches, AM1, PM6, like DFTB, that are getting really popular also to increase the large size and to add the statistical component that we want. So I focus on the possibility to launch several trajectories. In QMMM, I would say what you can, if you are doing DFT for a system reasonably large, you can go to 100 picoseconds. If you do, for instance, umbrella sampling. If you are using semi-empirical, you can go to microseconds sometimes. I will give you an example this afternoon. We will check a trajectory together. But what you want is perhaps not to have long trajectory, but really to be able to start from different points and to generate a bunch of them. And it's much more, there are much more examples from photochemistry, like the one I show here. And the reason for that is that here, I just need to stop at 200 femtoseconds. If I want to do an enzyme and I do an umbrella sampling, I need much more time than that for the trajectory. It's also important to note that I mentioned that you can try to reduce collective variable to redefine the reaction coordinate, but sometimes you also want to do 2D simulation and 2D free energy profile. And this is where semi-empirical approaches and DFTB are going to be able to give you this profile, where you cannot discriminate or just two independent coordinates to verify the fact that they both are implicated in the reaction and so on. So not one-dimensional, but seven-dimensional. And now comes the nice point. If you don't really like semi-empirical approaches or DFTB, there are different ways you can just improve the situation, because normally you want to study one reaction, which may have some anionic feature or just like the hydrogen transfer, for instance. You can just like propose a new semi-empirical approaches that would be just specific for this family, like the hydrogen transfer. This is what was done, for instance, by the group of Castellion. They just use a spline function correction to just like they have a specific Hamiltonian, they name it like AM1X, something like that, to just be able to catch up with the fact it was a hydrogen transfer. And then they can just correct by M062X or another functional on some every 50 points to be able to correct a little more and try to add the statistics provided by semi-empirical based QMMND, but going close to the accuracy of DFT MMND. And they are also over performance by DFTB3, so plus U to treat into account the metal, for instance, so taking into account the polarization. There is the tight binding of Grimer that works well if you have metallic system, because before when you have metallic system, you tend to say that it was the work of DFT and not so much wanted to do something different. There is one also good advantages about the semi-empirical approaches. Normally, when you do QMMMD, we have a sophisticated level at DFT. This is the case here in Dumont, UK, the one we will be using this afternoon. Normally, here is like a droplet of a solvent. To avoid diffusion, it's a little hard to cause the periodic boundary condition. So it's done in a sphere, and then you freeze here some solvent molecule just at the periphery of it. And then here, I'm just going to have a dynamic of the system, and then I look into here where the DFT. But I don't have periodic boundary conditions, so this would not be of any help, for instance, if I want to look at heterogeneous catalysis. Also, I'm limited essentially. So with DFT approach, normally you don't always have periodic boundary conditions. You always have them when you're doing semi-empirical approach. So in this next tutorial about Dumont UK, they also give all the lectures, so refinement, let's say, what they could do when doing auxiliary DFT and adding the polarization, which is also why it's not so much the problem here to have this problem of the frozen layer, and then it's embedding in a continuum to try to mimic, but you don't have to explicit, and it's not a fully periodic simulation. So there are different flavor of it, and I'm just going to describe one additional feature we could have perhaps in the future in the QMMM world. If you think about, sorry. So here is actually a code that we will be using, but you want to have, active water molecule, but it's a bit more solvent exposed than the classical enzyme, I would say. And we would like to have exchange of water between the QM zone and the MM part. Can we do that? It's actually extremely difficult. So I'm not talking about the link atom here, but just about typically water molecule. But I want to describe, like for my nitroxo compound just a little before, that we're interacting. But if I want to do dynamics more than a couple of femtoseconds, already at picoseconds range, I'm going to have exchanges between this licorice water, the big one, and the small one, and I want to be able to let them jump and redefine. If I just add an electron on a system, I'm probably going to change the solvation coordination quite significantly. Can I describe that in a simulation? Here is what was attempted by people that work on adaptive QMMMD. And it's a very challenging situation actually for numeric because it triggers numerical instability. So you have different code to do that, different QMM code, different MM. So the interface is really flexible. The problem is that if I want to do that, I'm going to have the happy life here between the experience, like the potential of the QM and the MM, and then I'm going to be able to say to this water molecule, it's time to jump to the MM world. But when I do that, there is a need to define an intermediate zone, but it's called the transition zone between QM and MM, where I'm going to have to introduce a correction. So it has a certain name, okay, but just to give a smoothing correction to be able for this MM water molecule to enter here, for instance. Go back to here, and then this MM1 to jump to there. So at this crossing point here, there is some numerical instability, and I need to be able to describe this situation for this molecule to enter. Oops, sorry. I told you digital pointer, it was a bit difficult. Okay. I want to have this one, and I want this molecule to enter the QM, so I'm going to have this situation, and then this one is going to leave for MM. And then you can see that in terms of energy, it's not very good. And when I derive force fields, I'm going to have instability. So there are some codes that are doing that, and they are really pioneering that. But this is something we want because we would like to have a truly accurate response from the solvent to a given electronic membrane. I wanted to stress out that about the system that we have been looking at together this morning together, there are many examples over like energy, charge transfer, proton transfer, hydrogen transfer. Everything about light, I let it to Igor just after. DNA formation and repair, also a very nice point that is more and more important, especially in the today's situation. You can really use QMMM for drug discovery. This is a review by Marco De Vivo. You can do that to improve the estimation that you have between protein and ligand. The idea being that in the QMMM description, you are just going to remove the parameterization of the ligand a little bit. So you may recover some accuracy from that. It has to be done. For one example is QMMM PBSA, but you can also do it with true free energy estimate if you are interested in, and that works actually. It's under review. People are going to assess that effect fairly recently, and it seems to be promising. Pharmaceutical companies are actually trying to look at that to improve the situation. I described some situations, find effect in solvation, and you will see that the problem is a bit different from the enzyme because I don't have a big mechanical effect and a big electrostatic effect, but I have some fine polarization that are truly missing. They begin to come to this world right now, but this is something where it's not routine and it depends on the situation. The solvation can be difficult, especially if you want to have dynamic. Radical chemistry, I give a few examples. I'm just going to mention zeolite. There are a lot of systems actually studied with zeolite, and you will see the partition can be not so easy. I'm going to cut a lot of silicia oxide bonds, but it's doable and it has convincing results here. Here an example that we have seen a little bit where I have very long photo-induced charge transfer with active residue, which have to be selected based on also the experimental evidence. I did not describe it, perhaps I will say here it's a little bit more historical, but if you want to do inorganic chemistry with bulky ligand, this is one of the situations where onium has been used quite a lot. I would say that now if you have a bulky ligand, you don't want to pay the price at the frontier. Here is an example I just grabbed from École. So we have here a carbon bond with different 3-phenyl, but you see when you want to cut here, it's going to be, it works, but perhaps not exactly something that people want to do nowadays. So if you have bulky ligand, perhaps you will not do it and just let it because the price of the QM part is not as significant so much anymore. If you want to train yourself with QMMM, now you have a complete palette of interface. It's really very huge. I tried to find a review for that, but recently I did not have any recent one, so here is my own one. A lot of QMM packages have an interface with ND packages, and now the trend is perhaps, as I was saying, to use the ND package that are going to call different QM codes. So for instance, Amber can be interfaced with Gaussian, Orca, also TerraChem. So it's really up to you to decide. So if you have a flavor in the QM package that you would like to get and to put in your QMMM, it's not so much of limitation. I did my arrow, I didn't put all the arrow, but and I have plenty of them, draw marks and so on. It's really up to you to decide. There are also some dedicated interface that like a ChemShell that can just are just going to be written just only to do QMMM. So then they have some advantages to some of them and so on. But you can have a lot of different ways that you want to do QMMM. And so the interface here, I could have basically, I think, draw a line between all of them. Some of them are widely distributed. I could have mentioned CPMD, for instance, okay, also CPQK. It's really like up to you, and there are some of them are really confidential, like the one that use Posen, Orbital, or sophisticated ski, and all the ones they are used by more and more people, which also explain, like as was showing the great number of publications. I wanted to finish with a bit of a good example also, just to give a taste. So taken from the recent literature. So this is a DFTB-MM metadynamics to show a proton transfer, because I didn't show many examples of proton transfer yet. Between here, you see between this negatively charged residue going here to the aspartate and then finishing up here to this other one aspartate. So this range from several angstrom of distance. and you can assign really accurately the different states that are going to be into place. So this has become something extremely reliable, and you can obtain this spectra also rather rapidly, because you can parallelize rather easily. I can give you a counter example where you do not need to do QMMM. I was saying QMMM, you can do it for protein ligand. Here is an example of a transport protein, but it's going to have a linoleic acid inside, and you can see here, or believe me, but there are a lot of hydrophobic residue that are surrounding this long chain that has nothing that is really charged, nothing that is really polar, just one here that is protonated because it's in gas phase. So for that system, you could do QMMM, but it will not improve the free energy, I would think, at all. And it will be much smarter, I think, to just like stick on different approaches that are rigorous, just to explore the free energy, but not try to have something like QMMM where there is no electronic phenomena that goes in. Okay? It could be useful if you have a metal and you want to recover a parameterization that is a little rough. So for instance, if you have lanthanide complex that are interacting with a protein, the parameterization of lanthanide can be done by things like NCPBA, but you may have difficulty when you want to check, you want to do NMR of it, then you are going to do QMMM to recover the classical parameterization that was a little tough and where you wanted actually to get the first idea of the diffusion process. Then you go on to restore some electronic phenomena. I'm reaching a bit of the conclusion here. So I try to show you, and that was part of the difficulty of this lecture. In QMMM, each system is really a different story. You can just like choose a QM size, the Lennon size, the difficulty in partitioning are quite different. So there is no universal way to do things. I should mention, even if I didn't yet play with that, but you can also think that in the future, this machine learning is going to be a game changer for QMMM. For instance, I grabbed this recent paper from the group of Lineker, and there is a solvated system here, like probably currently driven. And then they do this QMMMD, and they extrapolate the result just to be able to like get rid of this limitation that I say that you can just not sample as much as you want. So this is going to be something many recent work to alleviate this problem here. And it's also QMMM very useful to decompose energy and to design new environments for chemical reactions. So in enzymatic catalysis, for instance, the big gain would be to change substituent to be able then to go back to suggest new experiments. And QMMM has been so reliable that people just use it in, like, for instance, biological institutes like IBS in Grenoble or so on, to change, design new environment, and also to have protein mutants. So because you can just, like, for instance, give cell residue decomposition and say this one should be changed, like, for instance, in this example that I showed you here, the proton transfer is very possible that people can just neutralize one of them made by alanine and just being able to have numerical prediction. This goes to what I will be discussing with you this afternoon. So with that, I hope you get the key feature, taste a little bit of it before you go on to the exciting state with Igor Shapiro just after. Okay? Is there any questions?
A silly question. So you said that nowadays, so there are implemented ABCs for QMMMDs whenever you're using empirical methods, where it is difficult in the case you have EFD, and indeed you don't find a lot of software that has this. So my question is, what are the main difficulties implementing ABCs in EFD? Because for default, both methods are like self-consistent, let's say.
So Yeah, this would be about this slide, for instance, right? Like what would be, so I would say that perhaps it's not, it is difficult in the technicity, and this is actually described in this review. It's just that here the focus is really on the DFT, and because you don't have so much time of simulation, you won't feel the problem that much. So if you wanted then to go to higher time scale, then you will need the PVC, but here in their result, the problem is not yet there. So they would find a solution to go towards that, and I think there are some codes that do actually DFT, MMD with pedalic boundary condition. It's just that they did not reach the stage where it has become really the thing to be solved. Does it answer your question?
We have time. Can you comment a little bit more about the machine learning models and so on? Because as far as I know, the main drawbacks is like you need a lot of QM simulations to have like really nice potentials with machine learning, and the transferability is like quite difficult.
Yeah.
So yeah, I understand that can be really nice, but
yes,
you can do like really fast simulations, but
so the first result about that are really new here, and there is this thing that we don't know so much of the quality, but here what we want to assess is just a little bit the communication between the MM part and the QM part, but not replacing the whole everything. Okay, so it's just perhaps to have a better communication between the MM and the QM part, relying on machine learning, but not redefining like everything.
Okay, nice. Thank you.
Thank you.
Elise, can I ask you, do you think, I mean, the thing with the periodic boundary conditions is basically for, let's say, replicating the solvent, right? Interaction with the solvent. Yeah. Do you think that just to overcome the problem using implicit solution should be enough?
Usually not. I work on very electrostatic systems, so I can see also one thing I did not mention is that sometimes just like you can have allosteric effects a little bit, and you can have effect of communication of ions that are really far. So I'm not completely sure, but like for me, it was ever historically implicit solvent or QMMM, and bridging the two, it's done here. For instance, I know that for this system, sorry, I'm just going to. So here they use this one just to be able to mimic, but they would prefer to have the full PVC, because also you have the counter anion you may want to describe, even if they are little far, it's something we would like to capture. But on most of the cases, they are indeed the implementation with implicit that I give quite very good result. Okay.
Do you know any software where they are able to use 3 layers, maybe QMM, PCM or something like that, or not PCM, but any of the other implicit? So
when they rely on subtractive, you have quite 3-layer system. I usually, like for instance, Mulholland, the system that I showed, I think it's a 3-layer one, in a sense for me, because they're using IQM, intermediate QM, and then MM. But playing with implicit, Dumont UK has it.
Okay. So for questions?
This is a really curiosity. So you said that it doesn't have to do with the mix. So on the triplet timing radical system, so you said that you had a dynamics of 1 nanosecond. That was DFT. So you actually, I mean, how long did it take? Was it a QMMMD or?
It was QMMMD. So with the 4 timing in the part, we launched. It was 2 months, I think, on 16 CPU. Okay, but it was disappointing because we get 5 trajectory, and they're telling us something that is actually quite different, because there is this 50K cal on the triplet timing. I mean, if you compute it just the isolated timing, you will get extreme accurate result. And there, I wanted to show it's a case where you see that the QRL trajectory can give you something that is so different because of the starting point. But it's not, and I would say that the way we did it, you can do the example I showed from TerraChem, for instance, that is an excellent GPU implementation. You can really have a lot go much further, and it has impressed me a lot. Also, if you use array implementation, which we use for the triplet timing, this saves us a few months of calculation. Okay.
You compare Terracan with Orca, because I remember some time ago when I was with Leticia, we compare the performance of Orca with 4 CPUs was more or less the same as Terracan one.
Yeah, I think Terracan is more efficient, but if we use the array or Orca, I would slightly go for Orca. Because the array implementation is really giving a big difference. We sometimes use Terracan only for IAMD, but I'm not sure the QMMM is as performing. It's really comparable to the idea.
Okay, so Elise, thank you very much for your talk. Okay, so now coffee break until 11:40. It's great. Very nice. Why not? As soon as I go, I do well, let's say, obsessed with seeing Peter again. And one was the student, right? The outcome. So it was very good for exciting for that.
Sometimes the people are and you need the yeah.